The goal of this screencast is to show you how to use a reactor simulation in SuperPro Designer to solve problems involving reactions. So we're going to use the following example in which we're forming acid from salicylic acid and acetic anhydride, and you're given the reaction stoichiometry as well as a kinetic rate expression and other relevant data for our reactor system. Our goal is to determine the amount of salicylic acid after 2 hours of this reaction. So here's our form for SuperPro, and I've chosen a batch setup since we're doing a batch reaction. So the first thing to do is to designate our components that are going to participate in this simulation. So we could go to Pure Components under Tasks and Register. And we could look for the components that are involved, the salicylic acid, acetic anhydride, acetic acid. Here acetic acid is available, and we click on Register and add it to our list. However, the other three components are not, so we have to create them. So if we go to this magic wand up here, we could type in the name of the components that we're using, and we just click OK. And so I'll do this for the other two. And now we have our list of components. Since they are not in the original database that we're using, we have to add certain properties to them to help us solve this system. So if we click on salicylic acid either twice or through the Edit button in the top right, we could open up certain properties that we'd like to enter in. So we go to the physical constants, and we could type in a molecular weight of 138.11 and a normal boiling point of 211. We could type in other physical properties, but for this simulation it's not necessary. So we could go ahead and click on the physical t-dependent, since we do need the density, and we're going to use a density of 1440 and a b-value of 0, and say that it's not temperature dependent in this simulation, and click OK. We're going to go ahead and do the same thing for aspirin using molecular weight of 180.16 and a boiling point of 140. Again, we go to the physical t-dependent tab and click a density of 1400. Again, these are in grams per liter, and say it's not temperature dependent, so we set a value of 0. And then lastly, the acetic anhydride. It's important as you enter in this information to make sure you're using the right values for the right units, and since SuperPro has built-in units with each of these, it's good to check those. So now we've entered in all our components, so we could click OK. So the next thing to do is go to Unit Procedures and enter in our reactor. So we'll go to Batch Vessel in a reactor and add it to our sheet. So now we could also start connecting lines. This top line up here is our default input, and the bottom one on the right side is our default output. We're going to want to double click on these lines and add the components to each line. So we know we have acetic anhydride coming in, so we add this to our line, and we have salicylic acid coming in. So at this point we want to set our mass composition or our flow rate, and in this case in the problem statement we're told that they are entering at an equal molar ratio. So we'll click and make sure that we have the button for mass composition entered. So using the molecular weights and equal molar ratios, we could calculate what the mass fraction of each would be entering, and we could enter that in here. Now this button up here also can use specific concentrations of a component to calculate concentrations of other components if there are multiple species. So use that when you know the concentration of a component. So the other thing we want to do is set the volumetric flow. We're told that it's 2,000 liters per batch, and we'll use the temperature and pressure and everything else set as default. So we've set our incoming line. We now want to set the operations for the reactor. So if we double click on the reactor itself, we have our whole list of available operations we could use for this reactor. So we want to charge the system, so we click on charge and then add it. And then after charging, we want to heat the reactor, and then react using kinetic information, and then lastly transfer all of it out. So now what we're going to do is right click on the reactor, go to operation data, charge 1, and start entering in information. Now it's really important that you click on charge using and then set our line. We're telling the reactor what's coming into it. The other thing we're going to do is say that our setup time is 0, and we're going to calculate the process time based on our volumetric flow rate entering into the system. It's best to click on the units first, since that will automatically change. So we're going to use 2 meters cubed per second of volumetric flow rate entering our process. So at this point there are obviously other tabs that we could use, but for simplicity we'll just go to the next operation, which is our heating, And we're told in the problem statement that our final temperature is 350 Kelvin. We also are going to use our default heating utility of steam with 90% efficiency and a heating rate of 1 degree Celsius per minute. We click on the next button down here to go to our next operation, and this is where it starts getting interesting. We have our reaction. So let's set our operating temperature for the reaction at 350 Kelvin. We're going to select steam as the heat transfer agent. So going down here, double clicking on steam, so that's going to control the temperature of the reactor, and enter a reaction time of 2 hours, since that was what the problem statement asked us to determine. We have to set what our reaction looks like. Let's click on the reaction tab up top, and this icon that looks like a flask allows us to edit the stoichiometry. We know that acetic anhydride and salicylic acid are our reactants, and our products are acetic acid and aspirin. Now, for the stoichiometric coefficients, you could either use mass or molar coefficients here, and here should all be 1 to 1. So at this point, we click OK, and then we want to enter in the kinetic information. So we click on the R. We're told what the reaction rate is, which is 0.0059 for our K value, and then we're told it's first order in acetic anhydride and salicylic acid. So if we go over to the reaction order, for acetic anhydride we click on 1, and salicylic acid we click on 1. And that's it for our reaction rate. And you can see that our reaction molar stoichiometry is shown down below, so we could double check it. And then if we cared, we can enter in what our reaction heat would be so that we can start doing our energy balances. Since we're just concerned with our material balance in the statement, we'll keep it basic. Last thing after react is our transfer out. So again, click on the next operation, and it tells us that aspirin, there's no rate reference component. So I missed the fact that under R, we have to say that our rate is referenced to some component, since our K value is specific to something. So this is for aspirin. So that should fix our error. So lastly, on transfer out, pick our line, which is our products. We're going to say our setup time is again 0, and then we're going to say our process time is calculated based on our volumetric flow rate, which we said was 2 meters cubed per second. So you see that there's no next operation tab, so we're just going to click OK. We have everything designated. At this point, I would save the file, and then click Solve ME Balances. And as long as no error showed up, then you have at least the proper settings to run your simulation. It doesn't necessarily mean it's correct, so it's always good to check the values that you're getting. What we're interested in is looking at the product stream, so we could double click on that, and you could see what comes out of our reactor after 2 hours of our reaction. You see what the temperature and pressure are. You could also see the flow rates. Based on that information, we could see that our salicylic acid, roughly 6 kilograms per our batch, and we started with 1450 kilograms, so we could determine how much reacted and obviously answer the question of how much was left. So hopefully this gives you a basic idea of how to set up a reactor. You can see that there's a lot of tabs and buttons to enter in more information as you get more precise.